This is the first PowerPoint video on acids and bases. There are going to be three altogether. So in this video, I'm going to go over acid-base properties and theories, acid strength, and Kw, the constant for water, then pH of strong acids and strong bases. First of all, acids have a sour taste. They change the color of certain plant dyes, especially litmus, I guess. React with certain metals to produce hydrogen gas. Here's an equation showing hydrochloric acid reacting with a piece of magnesium, and we're getting magnesium chloride and hydrogen gas produced. You can also react with carbonates and bicarbonates to produce CO2 gas. And here's an equation showing hydrochloric acid reacting with calcium carbonate. We're getting calcium chloride, CO2, and water produced. And acids also are electrolytes. Now, strong acids are strong electrolytes, and weak acids are weak electrolytes. Bases, on the other hand, have a bitter taste. They feel slippery. Many soaps and detergents contain bases. They also cause color changes in plants, but different changes than the acids do. And they also can be strong or weak electrolytes. So strong bases would be strong electrolytes, and weak bases weak electrolytes. And down here at the bottom, we can see a couple of examples of bases. This is ammonia, and this is hydroxide, and here's somebody washing his dog. All right, now the first definition we're going to look at is called the Arrhenius definition of acids and bases. It was created by a fellow named Svante Arrhenius in around 1920. So according to Arrhenius, an acid is something that ionizes in water, producing hydrogen ions. Or we can write H3O positive, which are hydronium ions, but they mean the same thing. Now here's our example. We can see here's the HCl, it's supposed to be the hydrogen and the chloride, and here's the water, and here's our hydronium ion and our chloride ion. And we can simplify it by just eliminating H2O from both sides and wind up with this. Now, Arrhenius base is something that dissociates in water, producing hydroxide ions. That means that the base already contains the hydroxide ion, and the water is simply pulling it from a cation. Now, our example here is sodium hydroxide. But the thing is that the hydroxide already exists. We're not making it. Whereas up here, the hydronium or the hydrogen ion doesn't really exist yet until it reacts with water. So you need water for an Arrhenius acid. And for Arrhenius base, it can only be hydroxide compounds. Now here are examples of some other hydroxide compounds. Sodium hydroxide we see from the previous slide is Drano, which you could buy in a supermarket. Potassium hydroxide, also a very strong base. Barium hydroxide is even stronger. You notice we have 2 hydroxide ions per mole, whereas here we just have 1 of each. And then we have milk of magnesia. Now, same ratio for the formulas here, but the difference is magnesium hydroxide is a weak base, and it doesn't produce too many ions. It has a really small constant. Our second definition is called the Bronsted-Lowry acid-base theory. And here, acids donate protons to bases, and bases accept those protons from acids. So here's an example here. We have HCl plus water yields hydronium and plus chloride. Now you can see here that the hydrogen ion, now we're acting as if these ions are present in HCl, but they're really not there yet until the reaction happens. But this hydrogen here is going to come over and be captured by the oxygen of the water, and that's where the hydronium comes from. And the hydrogen is leaving behind its electron, and that's why we wind up with chloride ion. So the HCl is the acid because it's donating the proton to the water, and the water is the base because it's accepting it. Now here's another example where we're reacting something with water. Now in this case, if we look closely, you see that we have CO3 minus 2, and now it's HCO3 minus 1. So the CO3 minus 2 has accepted a hydrogen from the water. So therefore, that's the base and the water is the acid. Now we also have a reverse reaction because the carbonate doesn't react that well with water. Now reverse reaction, we also have an acid and base combination. So which one of these would be the acid, which one would be the base? Again, we have to look and see what it's becoming. So the HCO3 minus is becoming CO3 minus 2. So that's going to be the acid, and the hydroxide is the base. Now these guys are called conjugate acid-base pairs. So here's one conjugate acid-base pair, the carbonate and the bicarbonate ion. The other conjugate acid-base pair would be the water and the hydroxide. So what do we see here under this theory? An acid becomes a base and a base becomes an acid. An acid is a proton donor, a base is a proton acceptor. Let's see if you can complete these equations, come up with the products. I'm already telling you what's the acid and what's the base. Maybe you want to pause the video for a second and try to write down your products, and then we'll see the answer to it. Okay, here we go. For the first one, we're making hydronium and we're making nitrate ion. Now, because HNO3 is an acid, the H positive is coming from that. That's going to be donated to the water acting like a base. And down here, we have the opposite. Now the water is donated its H positive to NH3 ammonia. So ammonia is the base. Let's see if you can answer this question here now. What is the conjugate acid of HCN? And another acid, H2SO4, and the third acid, H3PO4. So again, maybe you want to pause the video and give it a try, and then we'll see the solution. Okay, here's the solution. So the conjugate base of HCN is Cn minus, because what we're doing is really just subtracting from this formula, taking away an H positive. Just one H positive now. So if we do that, we're lowering the formula by 1 H, and then we're also lowering the charge by 1. So here the charge is starting off being neutral, and so that's why we want to do with a -1 charge. And if you notice, the same thing is happening to these two. We're subtracting that H positive. Now what about this question? What is the conjugate acid of the following ions? You want to pause the video and try these. All right, here are the solutions. So in each case, what do we do here? So if we know that this is a base, then an acid, we're going to add H positive instead of subtracting it. So we're adding H positive to each of these formulas. And that's why we have the H over here now, and also the charge went up by 1. So it's -2 plus 1. Right, now this is something about the conjugates. Relative acid strength versus relative conjugate base strength. So if you have a very strong acid, that very strong acid has a very weak conjugate for a base. So as the acid becomes weaker as we go down the column, the conjugate base is becoming stronger. So HCl is a very strong acid, and so its conjugate Cl is an extremely weak base. Acetic acid is a weak acid, so its conjugate acetate is a strong base. HCN, hydrocyanic acid, is a very weak acid, so Cn minus or cyanide is a very strong base. Now let's take a look about acid strength anyway. What does it mean for an acid to be strong or weak? Well, a strong acid is 100% ionized, which means 100% of it reacts with water to produce ions. And we can see here, we're starting with HA before dissociation. It's really ionization. And then at the end, there's no HA left, it's just in the form of ions. Whereas with a weak acid, only about less than 10% of it really ionizes in water. And so you see we're starting with just HA, and we still have a lot of HA left and very few ions. So strong or weak really depends on the percent ionization. Strong acids are 100% ionized. Now, definitions of an acid, so far we've had Arrhenius acid, a substance that produces protons. Bronsted acid, something that donates protons. Looks like the same definition for those two. The difference is Arrhenius acids have to be in water. Bronsted acids don't have to be in water. They can be in other solvents. Now, the third definition is called a Lewis acid of electron dot symbols, or Lewis symbols. Remember him? Lewis symbol fame. So he's talking about a pair of electrons. Not talking about protons at all. So he says an acid is a substance that can accept a pair of electrons. So let's take a look at that. Now, a Lewis base is the opposite. They donate the electrons. So here we have H positive reacting with hydroxide. Now you see that pair of electrons can be donated to the H positive as we make water. So therefore the hydroxide is a base. The one thing I want to mention is that any substance that's an acid under the first two definitions is also going to be an acid under the Lewis definition. A substance that's a base under the first two definitions will also be a base under the Lewis definition. So what does the Lewis definition do for us? It allows many, many more things to be a basis than we had before. And we don't need water. That's our acid and that's our base. Now let's take a look at this one here. Now we have H positive and we have ammonia and H3. And here are a lone pair of electrons on the nitrogen atom in ammonia. And what can happen is those pair of electrons can be taken in by the H positive as it bonds to it. So this doesn't look like an acid-base reaction. We only have one product, but it is under the Lewis definition. Now here's another example. We have boron trifluoride. Now boron is one of these exceptions to the bonding rules where it doesn't form an octet, so it has a vacant orbital right here. And if we react that with ammonia, and you can see here's that pair of electrons again. So these pair of electrons can be donated to the boron. And what happens is they bond together and form a new product. That's our acid and that's our base. So that no protons are donated or accepted is really talking about pairs of electrons. Now, how about a metal? Now, we talked about before about metals reacting with acids. Here's magnesium reacting with hydrochloric acid, and we're getting hydrogen gas and magnesium chloride. Now, is magnesium a base? We know that HCl is an acid. So how can magnesium be a base? It doesn't have any hydroxide in it, so it's not an Arrhenius base. It's not accepting any protons, so it's not a Bronsted base. Now, if I take it apart, look closely. Here is the magnesium atom, its electron dot symbol, 2 valence electrons. And now I'm taking the 2 H's out of the HCl, 2H positive. So what can happen is this pair of electrons winds up going to the 2 H positive ions, and we wind up with then H2. And then we have a magnesium ion produced. So in a sense then, the magnesium is a Lewis base because it's donating a pair of electrons. Now the H positive was an Arrhenius acid and also a Bronsted acid. So that hasn't changed. So this is just a comparison of all three definitions together. And this is a good one for review. Right. Next thing, acid-base properties of water. Anytime you have water, you're going to have a few molecules breaking up into hydrogen and hydroxide ions. That's called the autoionization of water, kind of self-ionizing. You can put in 2 water molecules versus just one. And you see here we have one water molecule is going to take the hydrogen away from the other water molecule and making hydronium and hydroxide ions. And this is probably looks a little bit simpler, but that's what this equation up here is saying. 2 water molecules are in equilibrium with hydronium and hydroxide. Remember, this is the same as that. In fact, if I take this one and simplify it, that's what it would look like. So you want to remember, we're going to see this today, that H positive can stand for H3O positive. Now, let's take a look then. What if I have a solution where I have a lot of hydrogen ions? I'm going to have then a very small amount of hydroxide. So if my hydrogen ion concentration is greater than my hydroxide, this is going to be an acid. Now, if I have distilled water where those concentrations are equal, I have a neutral solution. And then if I have a solution where I have much more hydroxide ions than hydrogen ions, I have a base. So the thing to remember is, anytime you're dealing with water, you have both hydrogen and hydroxide ions present, regardless of whether it's an acid or a base. So how are the hydrogen and hydroxide ions related in a solution? Well, if you multiply the concentrations together, you get what's known as Kw, which is the constant for water. The value of it is 1 times 10 to the negative 14th. So let's take a look at a question where you're given the hydrogen ion concentration and asked for the hydroxide. How do we find out what the hydroxide is? Well, we're going to use this equation here. Now I'm going to start with this one where I've already replaced Kw with what it's equal to. And now I've also replaced the H positive from the information in the question. So all I have to do now is solve it for hydroxide. So I divide by my hydrogen ion concentration, and I get 1 times 10 to the negative 12th. Now, is this solution that is being described, is this acidic or basic? Well, that depends on which is greater, the hydrogen ion concentration or the hydroxide. Well, we can see here the hydrogen ion concentration is much greater, so this is acidic. All right, let's take a look at another question. Very similar. What is the hydrogen ion concentration when the hydroxide is 2.5 times 10 to the negative 4th? Is the solution acidic or basic? Maybe you want to try this one on your own and then come back and see the solution. Okay, here's the solution now. We'll write down our formula. We're going to make our substitutions and then solve for the H positive. So I'm going to divide both sides by 2.5 times 10 to the negative 4th. And I wind up getting then 4 times 10 to the negative 11th for my hydrogen ions. Now in this case, the hydrogen ion is a lot smaller concentration than the hydroxide, so the solution would be basic. Now you notice that the molarities of both hydrogen and hydroxide ions are really, really small. And they're so small it's hard to get a good handle on them. It's hard to relate to them. So a scale was developed by a fellow named Sorensen to make it a lot easier for people to use. And that scale is called the pH scale. So a pH is a measure of acidity, and this is its definition. It's the negative logarithm of the hydrogen ion concentration. And the P means power and the H means hydrogen ions. So a logarithm is an exponent or a power. So if you have a neutral solution, that means your hydroxide concentration is equal to your hydrogen ion concentration. Now at 25 degrees centigrade, this is the concentration of your hydrogen ions, 1 times 10 to the negative 7. And the pH would be 7. So remember, it's the negative logarithm of this value. Now, how are we getting one from the other? Well, you don't even need to use a calculator for this one, because the logarithm of 1 is 0, so that won't affect anything. The logarithm of 10 to the negative 7th is negative 7. And remember, in our definition, we want the negative of that. So a negative of a negative 7 is a positive 7. So Sorensen set up his scale so we always have positive numbers with his pHs. Now, an acidic solution, the hydrogen ion concentration is greater than the hydroxide. So let's say if we have a concentration greater than 1 times 10 to the negative 7, that means it would be something like 1 times 10 to the negative 6th, 1 times 10 to the negative 3rd. pH is going to be less than 7. So pH is less than 7 are acids, and the further from 7 they are, the stronger the acid is. Now for a base, it's the opposite. For a base, the hydrogen ion concentration is less than 1 times 10 to the negative 7. It could be as small as 1 times 10 to the negative 10th. What happens then? The pH will be greater than 7. So in summary, as the pH value goes up, the hydrogen ion concentration goes down. So here's our formula again. 1 times 10 to the negative 2nd, if that happened to be our H positive concentration, then the pH would be 2.0. And what I want you to see here is, why do I put down 0.0 and not just 2? And this is how we figure this out. We take a look at the value for the H positive. The number of significant figures in the H positive concentration will equal the number of decimal places to have in the pH. So there's only one significant figure here, so we have 1 decimal place in the pH. Here we have 2 decimal places in the H positive concentration, and then 2 decimal places. Here we have 3 significant figures, and notice 3 decimal places. And this is a nice little chart to show you how the pH in the H positive concentration vary. So when this is really, really small, that means your hydroxide is really high. And that would be a pH of 14. That's going to be a strong base. So as the pH number falls, the H positive concentration is getting larger. Here we are with neutral solution. Notice that's pure water. Blood a little bit greater than that. Milk a little bit less. Milk is almost neutral. Going down further here, vinegar is around a pH of 3, lemon juice in between 3 and 2, stomach acid is around 2, and then we even have a pH of 0, which is 1 molar HCl. Now once you're down this area here, we wouldn't bother with pH, we'd just be using the molarity of the hydrogen ion concentration. So pH is really developed when you're up around here or up here. These numbers are just way too small. Now here are some formulas that you want to jot down that we're going to be using in this chapter on acids and bases. This one we used earlier, and then we have this one for the pH. So those two we've already seen. Now here's another concept that we use once in a while with acids and bases. That's called the pOH. So just like the pH is a negative logarithm of the hydrogen ion concentration, the pOH is the negative logarithm of the hydroxide. Here's one that's also very valuable. How are H positive and pH connected like this? So if you have the H positive concentration in moles per liter, if you can convert that number to just a power of 10, then you're looking at the pH. Now, we use calculators to do the math on that one. And then we can do the same for the hydroxide concentration. And the last thing I want to add on is, if you add the pH and the pOH together, you get the number 14. Now this can be handy if you know one of these and you want the other. We just have to subtract the one we know from 14, and we're done. All right, so here's a question we can answer. What are the hydroxide concentrations, hydrogen ion concentrations, pH and pOH of 0.025 molar HCl, a strong acid? So here's our equation for the reaction. Now initially, remember from equilibrium, initially I'm starting with 0.025 molar HCl. I have no products then. My change, my HCl will go down by X and my products will go up by X. Now at equilibrium, I have no HCl left, and you notice that my hydrogen ion or my hydronium ion concentration is the same as what I started with. So you don't have to go through this all the time when you have a strong acid. If you had a weak acid, you'd have to go through this. But a strong acid, we're going to make an assumption that the molarity of the acid is going to equal the molarity of the hydrogen ions. So all we really had to do, if I wanted to find the pH, is simply take the molarity of the HCl and find the negative logarithm of it. That's what I'm going to do now. So here's my formula. I find the negative log of that, and I get 1.6. You want to try this with your calculators. Some calculators you have to put the log sign in, hit the log function first, then the number. Others you put the number in and then hit log. Now for the pOH, we just have to subtract 1.6 from 14, and we get 12.4. Now what about to get the hydroxide? So I'm going to use this little equation here. So if I want to get the hydroxide, all I have to do is say 10 to the negative pOH. Now this is the pOH here. So it's 10 to the negative 12.4. So how do I go from this to this? Well, I'm going to use the antilog. The antilog on my calculator, which is the 10 to the x function. So I just have to tell my calculator that I want x to be negative 12.4, and then that would be the value. You notice anyway, if the pH is 12.4, the hydroxide is pretty close to that as far as that power of 10. So like negative 12.4, negative 13, pretty close. All right, here's another question. What is the same thing? What are those four values for 0.50 molar sodium hydroxide? Now, sodium hydroxide is a strong base. So here's my equation. I'm going to write down ice again, but I don't need to do this for strong bases really anymore. My change, and you notice then, same thing. My molarity of the sodium hydroxide was equal to the hydroxide concentration. Same number. So all I have to do then is really take the molarity of the NaOH and find the negative log of that, which I'm going to do, and that gives me the pOH. So I have the pOH is 1.3, then the pH must be 12.7, and then I'm going to find the negative, the antilog, so I'm going to be using my 10 to the x function down here. Again, that's the antilog or the inverse log, and I get my value. So you can play around with these. You can find these in different orders depending on what you're given. So when we're given a base, we find the OH first, then we get the POH, then we get the pH third, and then lastly we get the hydrogen ion concentration.